For over 60 years, we've been pointing our most powerful instruments at the very top of our atmosphere. And for 60 years, it's been sending back signals that, well, just shouldn't be there. Today, we're going to unravel a scientific puzzle that's been hiding in plain sight. A story of phantom waves, a broken rulebook, and the new physics that finally makes sense of it all.
So let's get right to it. Here's the core mystery. Our best radars are constantly detecting these plasma waves way up in the ionosphere. But when we go check the math, the fundamental laws of plasma physics, it tells us, plain and simple, that under most conditions, these waves have absolutely no right to exist. And this is what we're talking about. This beautiful, spiky mess is a spectrum of those signals. The big peak in the middle is called the ion line, and those smaller ones flanking it are the gyro lines. We've been using these signals for decades to measure our atmosphere, but there's always been this nagging problem. Our own theories couldn't actually explain why they were so reliable.
So that's the big question, right? What if these signals, the very bedrock of so much atmospheric science, were basically scientific ghosts, waves that showed up to the party even though their names weren't on the guest list? How do you even begin to solve a puzzle like that?
Okay, to really get why these signals are such a big deal, we first have to look at the rulebook. Let's dig into how a perfect plasma wave is supposed to behave, according to the physics we thought had all the answers.
Let's start with a really simple analogy. Picture a couple of masses hooked together with springs. If you give them a little push, they don't just jiggle around randomly. They fall into these very specific, very stable patterns of vibration. And if you graph those vibrations, you get these beautiful, sharp peaks. Those are the system's natural frequencies.
In physics, we call this a normal mode. It's the system's own natural, self-sustaining rhythm. Think of it like striking a bell. It rings at a specific, pure note. That vibration is baked into the bell itself. And that's exactly what physicists were looking for in the plasma.
So how do you check for a normal mode in a plasma hundreds of kilometers up? You can't exactly fly up there and ring it like a bell. Instead, you use this incredibly powerful mathematical tool called the dielectric function. You can think of it as the official gatekeeper for plasma waves. It decides which waves are allowed and which ones aren't.
And the rule is actually pretty simple. First, you calculate the function for the specific plasma you're looking at. Then, you look for a root. That's a point where the function's value hits exactly 0. If you find a root, bam, the theory gives you a green light. A perfect, self-sustaining, normal mode wave is allowed to exist. But if there's no root, the theory says, sorry, no wave for you.
Right, so we have our rule. Find a root, you get a wave. Simple. Except this is where the story gets really interesting. Because when scientists applied this very test to that big, strong signal, the ion line, the rulebook completely fell apart.
Take a look at this. This is the math in action. See those colored lines? That's the dielectric function for the ion line. The horizontal line running through the middle is 0. Now notice how those colored lines dip down. They get really close, but they never actually touch or cross the 0 line. That's the whole problem right there. There is no root, so there should be no normal mode. There should be no wave.
And yet, nonetheless, the ion line is always observed. This line from the paper just perfectly sums up this 60-year-old contradiction. The math is screaming no, but the sky is screaming yes every single time we look. That signal is just there.
And to put a number on it, the theory only says a wave is possible if the electron temperature is more than 3.5 times the ion temperature. In the real-world ionosphere, that condition is almost never met. So this isn't a theory that fails once in a while. It's failing pretty much all the time. The signal we see every day simply shouldn't exist.
So what do you do when your observations and your theory are in a fight that's lasted 60 years? Well, this is where the genius of this new research comes in. What if the problem wasn't the signals? What if the problem was our definition of a wave? What if we've been looking for the wrong thing this whole time?
Let's jump back to our spring analogy. Remember how we just gave it one little nudge? Okay, now what if, instead, we're constantly shaking the whole system? It's not just ringing freely anymore, it's being continuously driven by an outside force. The new idea is that the plasma is just like this. It's constantly being shaken by the chaotic thermal motion of all its individual particles.
And that one idea changes everything. The old way, we were looking for roots, those perfect zero crossings, which meant we were looking for a perfect, self-sustaining ring. The new way, we stop looking for 0. Instead, we look for minima, the point where the function gets its lowest value, even if it's not 0. This lowest point tells us the frequency where the plasma has its strongest forced response to all that background shaking.
This gives our phantom signal a new name and a new identity. It's a non-resonant wave. It's not a perfect, natural ring. It's more like a strong, forced hum, a vibration that only exists because it's being constantly driven by the motion of the particles around it. It wasn't a ghost after all. It's just a completely different kind of wave.
But here's where it gets really cool. This new idea doesn't just solve the big mystery of the ion line. It also cracks another, trickier puzzle that has to do with those other little signals we saw, the gyro lines. Let's see this new theory in action. For years, this has been a real head-scratcher. On the left, you've got the gyro line signal seen by the legendary Arecibo radar. It's kind of weak, kind of broad. But on the right, you see the same signal from the EISCAT radar in Scandinavia. And whoa, it's incredibly strong and sharp. So what's the deal? It's the same kind of signal in the same atmosphere. Why the huge difference?
The answer, it turns out, is in the radars themselves. Arecibo operated at a higher frequency than EISCAT, and just like tuning a radio, that different frequency means it sees the plasma in a different way. This changes a key physical value, and the end result is that Arecibo created a large Larmor Radius parameter, while EISCAT created a small one.
And boom! This is where the new theory just clicks everything into place perfectly. At Arecibo, that large parameter made the conditions all wrong for a root to form. So what did it see? A weak, broad, non-resonant wave. But at EISCAT, the smaller parameter created the perfect conditions for a root. So what did it see? A strong, sharp, honest-to-goodness, resonant, normal mode. The puzzle is solved. The theory perfectly explains why the two radars see such different things.
So what this discovery really gives us is a whole new playbook. It's a complete and, more importantly, correct rulebook for classifying all the signals humming away at the edge of space. And this table here lays it all out. It's a new, unified framework that has a place for everything. You've got your classic normal modes that need a true root and give you sharp lines, like those strong signals at EISCAT. Then you've got the non-resonant modes that just need a minimum, and they give you those broader lines. That's our phantom ion line, finally explained. And it even accounts for a third type, these distribution-driven fluctuations, which is basically the faint, noisy background. It's the whole picture.
Which brings us right back to where we started. Remember that first spiky spectrum? Well, now, armed with our new playbook, we can finally understand the whole thing. The sharpest peaks, those are normal modes. The broad, ever-present ion line, that's a non-resonant mode. Even the lumpy stuff in between has a name. Every single peak, dip, and shelf is finally accounted for. We've turned these phantoms into physics. And this isn't just about cleaning up the textbooks. A more accurate model means we get better data about our upper atmosphere, which is crucial for things like protecting satellites and making sure your GPS works.
So we end on this thought. For over half a century, we've been using these signals as a workhorse tool without ever fully understanding what they really were. It just makes you wonder, doesn't it? What other cosmic whispers, from our own planet to the furthest galaxies, are we listening to right now, but are only just beginning to truly understand?